Okay, all set.
Okay. Okay, we are
all right.
We are happy to have Tim here. Okay, you can take over.
Thank you very much. I am very sad not to be seeing you all in person, which is what I was hoping to do, obviously. But I'm happy that we are at least having this virtual version of the seminar. So what I'm going to talk about today is some work that I've done actually over the last couple of years about modifying QCD cosmologically. This is the actual strong nuclear force QCD, the SU3 of the standard model. And the main application is going to be towards the baryon asymmetry of the universe. I'll also spend some time introducing that as well. And you can see in the bottom corner of the slide some of the references to some of the work I'll show here. It's mostly actually based on the first paper listed with Shada epoch, but there are some things from further work that we did with Juna Kroon and Jessica Howard, who was actually a UC Davis undergraduate, now that I think about it. And then later work with Dylan Berger and Michael Waterbury, who are two other graduate students at UCI right now. So the invitation, the sort of thing that gets me inspired here, is looking at sort of what we know about the cosmological history of the universe. We have a lot of information that gives us a pretty clear picture of what happens from the time of BBN onward. Measurements of BBN itself, the cosmic microwave background, those pretty much pin down the universe to a reasonable degree. I mean, there are still questions that need to be answered and room for some surprises, but we have a reasonable picture of the universe back to the time of BBN based on the fact that it works. Earlier than that, our information is basically driven by taking the standard model of particle physics and then extrapolating it backwards. We think that around a GeV, there was a QCD phase transition when quarks and gluons stopped being the right description for the universe, and it cooled down enough that it was instead described by hadrons. And even further back than that, we think that there was an electroweak phase transition where the electroweak symmetry was broken. Dark matter freeze out, depending on the dark matter mass, is thought to have perhaps taken place somewhere in these intermediate scales. Of course, it may be that the dark matter didn't freeze out or its abundance was explained some other way. And there's a need to generate a baryon asymmetry, and so baryogenesis should have taken place somewhere as well. I put it around the electroweak scale, but of course it could have also happened at a much earlier time if it was a model like leptogenesis. Also, please feel free to jump in and interrupt me with questions. I do tend to turn talks into monologues. I'm sorry about that. So if you interrupt me, I won't be offended at all. So here's an outline. I'll spend a little bit of time reminding us about the baryon asymmetry of the universe and some of the ingredients in the standard model that address it, because I'm going to be using those ingredients later on. I'll then connect the baryon asymmetry to the strong CP problem. This is actually an old idea from the early 1990s. And it's actually very similar, with one very important exception, to what I'm talking about today. And so it's actually useful to just go through it and understand that potential solution and why it doesn't quite work, but it gets very close. Then I'll actually move to the main thing that I've added to this story, which is trying to modify the theory so that QCD undergoes a phase transition such that it confines it around a TeV. Of course, eventually it will have to do something to quote unquote go back to normal. So eventually it will have to go back to either being deconfined and then it will reconfine again at a GeV, or maybe it's possible that it just kind of stays confined but lambda QCD itself evolves. And then I'll finish up with some outlook in future directions. So the matter-anti-matter asymmetry of our universe is pretty famous. Experiments put all together show that we have something like about 10 to the minus 10 imbalance between baryons and antibaryons, and that's normalized to the entropy density. There's a large number of pieces of evidence that are consistent with this picture. So one of the very simple ones is just the fact that cosmic rays contain about 10 to the minus 4 antiprotons compared to protons. And this is consistent with the idea that basically the universe is not made of antimatter, but it gets produced in rare high energy processes that are going on in different parts of it. Another piece of evidence is the fact that there are baryons or matter at all. The density of hadrons in the universe is such that if there had been equal baryons and antibaryons, we expect they would have annihilated into things like pi plus, pi minus, and gamma gamma, and frozen out to a much smaller density of around 10 to the minus 20. So just the fact that there is matter at all is in some sense an indication of a baryon asymmetry. But of course, the really rigorous and quantitative measures of the baryon asymmetry come from BBN and from the cosmic microwave background. So this is a famous plot that I took from the PDG. What it shows is as a function of an assumed baryon to photon ratio, eta, that's that same parameter as that was there before. So in other words, as a function of the asymmetry in baryons normalized a certain way, what you would predict in each panel for helium-4, deuterium, helium-3, and lithium-7. So theoretically, using the known nuclear physics, all of these abundances primordially can be predicted as a function of that primordial asymmetry. You get the colored curves that you see on the plot, and then shown as the yellow envelopes are the measurements of those quantities. You can see that there are pretty big error bars on helium-4 and also on lithium-7. It may be hard to see, but there's actually a very tiny yellow envelope that overlaps with the blue curve for deuterium. It's actually the best measured of these things and the one that really anchors the value you get from BBN. And then also shown and completely in agreement with that measurement of deuterium is what you would get from the CMB, which I'll talk about on the next slide. There is some tension with the lithium-7 abundance. It's got a big error bar. It's far enough off that one could make something out of it if one wants to. I don't have anything to add to this story, so I'm not going to today. It's also close enough that you could take the attitude that it maybe is just some systematic or even just actually a statistical fluctuation. And so that's sort of the place that I'm looking at right now, though I do think it is interesting to work on it. So this is another actually old plot. I like the old plots because they illustrate the physics. Now things are very precise, and it's very hard to find a plot that actually shows you to your eye what would happen and how things would go wrong if you change the values of the fundamental cosmological parameters. But so this is the famous CMB temperature fluctuations as a function of the multipole. This actually one is from WMAP because that's how far back I had to go to get a plot that I liked. You can see the WMAP data is the blue dots. Of course, it's been superseded by the Planck data that is much more precise. But what's nice about this plot is that you can see both the central value of eta and what would happen if you made it 50% higher or lower as the red and green curves. And it's very clear that the data actually prefers the value that we see. So the point is that also by looking at the peaks of the CMB, we can see, get a measure for the number of baryons in the universe. So this question of why the baryon asymmetry exists is really a question for particle physics. It could be that it's an initial condition of the universe. That would have been very mysterious, but possible, but also probably not consistent with inflation. Inflation erases all of the primordial abundances and then regenerates them, typically thermally. So as a, there's something that we need to do to generate a baryon asymmetry after inflation has already wiped out whatever was given to us by the initial conditions. As an input to nucleosynthesis, the baryon asymmetry must be generated by scales around a GeV. You could perhaps push that down to maybe 10 MeV or so, but I think that's pushing it. So it's really a problem for particle physics to solve. And famously, the three conditions to generate a baryon asymmetry, if I start from a baryon symmetric starting point, were enumerated by Sakharov. They boil down to, I must have baryon number violation, I must have both C and CP violation, and the universe has to go through a period that's out of equilibrium with regard to those two symmetries. Otherwise, I'm not going to generate an asymmetry if my starting point is symmetric. So at first glance, making baryogenesis work at the weak scale looks kind of dangerous. You need to have reasonably strong baryon number violation, but when we look for things like that at low energies, say mediated by irrelevant operators, we don't see any signs that something like this is happening. And of course, the very famous baryon number violation testing process that we look at is proton decay, which we've been looking at for decades now. You could imagine it's mediated by something like a dimension 6 operator, like the one that's illustrated here. It allows the proton decay into a pi 0 and an E+. Of course, this is just an illustrative example of a decay that could happen. The lifetime one gets can be connected to the scale of the new physics. And then when contrasted with the experimental limits of 10 to the 30 years, you find out that you need to have the scale of the operator slightly larger than the gut scale, large enough that the gut scales are in fact somewhat in tension with it, though not so discrepant that you would give up on them. If you were to say, imagine that maybe processes that change baryon number by 1 unit are not allowed, but 2 units are allowed, you would actually still get constraints from neutron-antineutron oscillation that would be around 10 to the 12 GeV or so. And that's actually still pretty tight. So it still sort of seems to forbid there being any baryon number violation at any temperature scale as low as the weak scale. Of course, the standard model already has a way of solving this problem for us. And that's because the electroweak instantons of the standard model violate baryon and lepton number. They preserve B minus L, but violate B plus L. And you could sort of think about this as something like a meta vertex, like the one drawn here. It has one left-handed quark of each color and each generation, and one lepton of each generation, one lepton doublet of each generation. And so these processes look like they destroy 3 quarks of each family and 1 lepton of each family. They preserve B minus L. Actually, because the neutrino masses are so small, they preserve B minus the L in each lepton family effectively, though eventually the neutrino oscillations will mix up the lepton number and make that not true. And this is not something I'm going to make use of in this talk, but it's an interesting fact that sometimes you can get some mileage out of. And the sphalerons also naturally explain the paradox of strong baryon number violation at temperatures around 100 GeV, but very small rates in low energy tests. At low temperatures, when the electroweak symmetry is broken, the masses for the W and Z imply that it costs a lot of energy to form the Sphaleron configuration. The Sphaleron rate is exponentially suppressed at low energies, and it's basically unsuppressed once the electroweak symmetry is restored and the VEV goes to 0. This basically lets us have fast baryon number violation at around 100 GeV or a TeV, while still having very little that we could measure today, explaining the searches for baryon number violation that we have not observed so far. So put all these things together, and the standard model actually has the ingredients in principle that were necessary to give us something like baryogenesis at the weak scale. And the idea is that when the Higgs actually develops its VEV at a temperature of around 200 GeV or so, we start off in the unbroken phase where the VEV is 0. If the phase transition is first order, we nucleate a bubble of the broken phase. That bubble then expands because it's energetically favorable for it to do so. As it expands, the sphalerons are able to violate baryon number and lepton number at the right outside at the surface of the bubble. But then as anything that it generates falls into the bubble, it remains. They're switched off inside the bubble, so there's the out of equilibrium process as that's happening. And there has to be some CP violation, of course, which can induce the asymmetry at the surface of the bubble itself. And it almost works. There are 2 sort of problems that let the standard model not explain the baryon asymmetry. The first one is the strong connection between Higgs physics and the electroweak phase transition. If I look at the Higgs potential and its thermal corrections, I get an expression like this one that's printed in a sort of schematic form in the middle of the slide. There's a tree level potential, which just says there's a VEV at low temperatures. And then there are some temperature dependent corrections, and they depend on all the species that are active in the plasma at the time, or in other words, the temperature that I'm interested in. And basically, because their masses depend on the Higgs VEV, this effectively turns into a correction to the Higgs potential. If I want a first order phase transition, there has to be a small Higgs quartic interaction such that the Higgs mass would be less than about 50 GeV or so, right? And remember, the standard model relationship is that the Higgs quartic is actually the thing that tells you what the Higgs mass is in the standard model. 50 GeV is not consistent with the LHC observations of the Higgs at 126 GeV, but it's actually fairly close. It's close enough that you could imagine theories that do nothing more than maybe add some extra fields that couple strongly to the Higgs could be enough to make this picture viable. And the MSSM is a famous example, which still works at some level if you hold your nose a little bit. The standard model also doesn't have enough effective CP violation in the CKM matrix. So it also would not, even if I were to fix up the Higgs potential such that I were to get first order phase transition, I still actually wouldn't quite generate enough baryon asymmetry because the CKM phases are too small. So what I'm going to do is now get sort of past the standard picture and talk a little bit about things that are closer to what I've been working on. And that is to try to invoke a different source of CP violation, since I know CKM isn't strong enough. There's an interesting question, which is, if there were a strong CP phase, maybe canceled by an axion or something, could I actually use that phase as a source of CP violation for baryogenesis? And this was looked at by Cosmological et al. In the early 90s. That was a paper I referred to earlier. The basic idea is I write down some raw theta bar term that here I've decided to put entirely into the coefficient for GG dual. Of course, in the standard model, the neutron EDM requires that theta bar is less than about 10 to the minus 10 or so. So it's actually totally irrelevant from the point of view of cosmology or anything else. But the key observation is that if there's a dynamical solution to the strong CP problem, such as, for example, the axion, the effective phase could be different in the early universe before the axion reaches the minimum of its potential. And of course, the axion and the Péchet-Quinn solution to the strong CP problem has been studied for quite some time now. The very last equation here shows schematically what one would get if I were to introduce an axion, which would then end up with a potential that would induce it to cancel theta bar in the usual way. So this is a picture of what one could imagine the relevant temperatures and therefore timescales are. So the magenta curve shows the rate of the sphalerons. They are strong. They're very active at temperatures above the electroweak phase transition. So I should actually tell you that on the x-axis, what's plotted is labeled as temperature, but think of it as time increasing. So the early universe is, you know, at the 0 of the axis, and then as the universe cools down, eventually I get to the electroweak phase transition, T electroweak. It cools down some more. I eventually get to the QCD phase transition, TQCD. So then the magenta curve is showing me something about where the sphalerons are active. They're active basically until T electroweak, and then they become negligible. If I have a theory that has a raw theta bar term that is then canceled by an axion, the axion potential doesn't turn on until QCD confines or thereabout. So that's actually indicated by the blue line, which shows you what the effective axion mass is. It's very close to 0 at high temperatures. And then as QCD starts to get strong, it actually turns on and the axion feels a potential and it is able to realize that it wants to cancel off theta bar. And so the effective theta that the universe sees, therefore at early times, is just some non-zero value, whatever value happened to be living in the Lagrangian for theta bar. But then once I get to around the QCD phase transition, the axion realizes it has a potential, its VEV shifts, and the effective theta gets canceled by the axion, such that strong CP is not violated today. So actually the axion theory is already one in which you expect the properties in early times, cosmologically, to be rather different from the properties today. Strong CP violation could actually be very much a thing, very, very effective in the early universe, and still be completely switched off today. So the challenge to use the strong phase together with the sphalerons as a way of generating a baryon asymmetry is the mismatch in the two temperatures. The sphalerons are only active above T electroweak, but the out of equilibrium condition I need is going to be generated by the axion rolling to its minimum, and that doesn't happen until down around TQCD. So basically, I have all the right ingredients, I just don't have them at the right time. And then the solution that Cosmological et al. Explored, which was also actually sort of presciently foreseen to some degree by Witten about 10 years earlier, was a supercooled electroweak phase transition, where instead of having the electroweak phase transition happen at about 100 GeV like it does in the standard model, it gets delayed, and it actually gets delayed all the way down to about the QCD phase transition. That means that now the sphalerons stay active longer, and they're active basically up through the point when the axion mass becomes non-negligible and theta effective starts rolling. So everything sort of comes together at the right temperature, and that temperature is around the QCD phase transition. So what I'm gonna do now is go through this picture and explain how this generates the baryon asymmetry, give you an estimate for the baryon asymmetry. Ultimately, this is not exactly what I'm doing, but on the other hand, it's very, very close to it such that I can then use like 95% of the infrastructure and to get my answer. So what I'm going to look at then is this theory by this picture by Cosmological et al., where the electroweak phase transition is supercooled, and I'm going to show you how that generates a baryon asymmetry through the rolling of the axion. So this is a model of spontaneous baryogenesis. And the basic picture is that the non-zero theta effective looks something like a tadpole for GG dual. That tadpole is related to the effective theta that I see at any time in the universe. A tadpole for GG dual is also a source for WW dual. So this is, again, very schematically shown by this diagram where I have GG dual on one end and eta prime exchange, and then WW dual at the other end. Now, that's a very fuzzy way of looking at it because I'm talking about a time, say, before QCD has confined. And so the eta prime is not really the right degree of freedom. You should really think about this as being a loop of quarks that carry the quantum numbers of the eta prime and therefore mediate information between GG dual and WW dual. So in effect, there's a term in the effective Lagrangian that looks like GG dual coupled to WW dual. It has, again, if I'm thinking about in the confined phase, it can be related to things like F pi and the mass of the eta prime, since that's the thing that is dominantly mediating the interaction. And the point is that when I put in then the vacuum expectation value for GG dual, this effectively looks like a tadpole for WW dual.
All right, sorry, can I ask a question?
Yes, please.
I'm trying to understand the formula like the theta effective look at tadpole. So how to see easily this formula? Why theta effective is equal to this one, this vacuum interaction value, JJ tilde?
I mean, so basically, if I have, if you think about the effective Lagrangian, if theta effective is non-zero, then what I have is a term in the Lagrangian that just looks like a tadpole for GG dual. It's just GG dual times some constant.
Yes.
So that's basically why. Right, so you can imagine that in the effective theory, it's easier to think about this in terms of the confined theory at low energies, right? The confined theory must have some potential terms that also go like, say, the condensate GG dual squared, GG dual to other powers, right? We know that actually, well, let me not go there actually. So you put those things together, and the fact that there's a linear term in GG dual effectively induces GG dual to take on a VEV to try to minimize that potential.
Oh, okay. Let me understand correctly. If I add some UV scale before the QD confinement, my Lagrangian is theta JJ tilde, right? You're trying to say this physical effect can be studied by going to the low energy after QCD confinement. The JJ tilde has a vacuum expression value, and this is CP violation source corresponding to the IR theta effective, right?
That's right, and I didn't actually do a great job of explaining why I kind of jumped from the UV description of QCD to the confined description of QCD, but that will hopefully become clear in the next.
Okay, I got it. Thank you.
Okay, so then going to the last equation that's on this slide, there's a set of constants that are related to theta effective and then the properties of the eta prime that I'll call the susceptibility as a function of T. And then there is WW dual, which of course we know is related to the divergence of the baryon current. So if I integrate this term by parts, the term, sorry, was there a question? No, I guess not. I probably heard an echo of myself or something. If I integrate this term by parts, the term that comes from the time derivative actually then becomes a chemical potential for the baryons. So integrating by parts, the piece that goes like d by dt moves the time derivative over to the susceptibility, and then this multiplies the baryon number current, the baryon number, and then thus induces baryon production. So again, mu effective, right, this effective baryon chemical potential is just related to that susceptibility on the slide before, taking its time derivative. The only thing that's actually changing with time here is the axion mass and sign theta effective, right? Everything else is a constant. And this is also sort of clear why I need to be living or need to be thinking about the time when the axion is rolling to its minimum, because it's at that period where these things have a non-zero time evolution. So then taking this chemical potential and using the rate of baryon production, I can calculate the number of baryons that are produced while the axion is rolling to its minimum. It's given by the expression in the middle of the slide, and then plugging everything in, making some simple estimates for how fast the sphalerons are. So this is an expression that's sort of appropriate for high temperatures, right before the Higgs Vev is turned on. And then the other constants that we've seen so far, including the axion mass, which also has some temperature dependence, it's pretty strong. We can then arrive, sorry, let me stay on the slide. We'll then arrive on the number of baryons that get produced during this transition. So what Cosmological and all had in mind was that they were going to engineer a supercooled electric phase transition by invoking a Coleman-Weinberg potential for the Higgs. This actually still seemed like an option in 1992 because we didn't really know anything about the Higgs boson back then. Today, you can still actually get to something that's similar with a modified Higgs sector. There was some work that was done a couple of years ago by Geraldine Servant and some collaborators where they used a RS composite Higgs model. There are also other options as well. The point is they just engineer a potential such that the barrier between the symmetric phase where the Higgs Vev is zero and then the broken phase is big enough that, even as low as temperatures around TQCD, there hasn't been enough time to tunnel through the barrier. So the idea basically is you've got this really big barrier between where you start off in the expectation value of Higgs equals zero, and where you want to end up at low temperatures, such that you will eventually tunnel there, of course, because it's at lower energy, but you just haven't had time to do it yet. And that persists basically. So you get stuck in this unbroken phase of the electroweak theory because of what you've done to the Higgs potential. And that persists until the temperature of the QCD phase transition, which actually completely changes the picture because the QCD phase transition breaks chiral symmetry. And therefore induces a quark condensate. So what the picture that Cosmological and all have is that they've changed the Higgs potential so that I never tunnel to the true vacuum during the time that QCD is perturbative. And then when QCD confines, it actually induces a chiral condensate, a QQ bar expectation value. There are 6 massless flavors because electric symmetry is still exact at this moment in time. And for 6 massless flavors, this is expected to be a first order transition. There were some arguments by Pisarsky and Wilczek in the 1980s that said basically that if you had 3 light fermions or more, you should get a first order phase transition. People have done a lot of studies on the lattice, and that's what this diagram is supposed to be a schematic indication of, to study this for 3 flavors where one of them is massive. And what you can see is that you do get a first order phase transition if all 3 quark masses are 0. That's in the lower left corner of the diagram. You also actually get a first order phase transition in the case where there are no quarks, when all the quark masses go to infinity. We happen to live in a place in the middle where the strange quark is light, but not light enough to put us into a first order phase transition. And so we still live close to a crossover point. So this is a first order phase transition in Cosmolo's picture. And this phase transition breaks the electroweak symmetry because the QQ bar condensate itself breaks the asymmetry and also looks like a tadpole for the Higgs field. And so that actually then even triggers quark masses and so forth. So the basic picture is that at the time of the QCD phase transition, the universe had started out, because of my modification to the Higgs potential, where the deconfined phase in terms of quarks and gluons, right, had no chiral condensate. So the expectation value of Q bar Q is 0. The expectation value of the Higgs is 0. Then I nucleate a bubble of the confined phase. It's a first order phase transition in this case because all 6 quarks are massless. In that case, I induce a QQ bar condensate that's of course of order lambda QCD. And that then triggers the Higgs to take a non-zero expectation value as well. So inside the bubble, I have both hadrons and also electroweak symmetry breaking. And that's basically everything that they needed. So now I can just plug in to my previous formula for the baryon, the number of baryons that I generate. It again depends on the initial value of theta effective. It depends on some of the hadronic properties of the pions and the eta prime. It depends on the electroweak Sphaleron rate, which goes like alpha weak to the fourth times the temperature cubed, right? In this case, it's the temperature of QCD. And then that last factor of lambda over TQCD to the seventh is coming about from the temperature dependence of the axion mass, right? Which also controls how fast the axion is rolling, basically. Now, at the time that you go through this phase transition where you both confine and break the electroweak symmetry, it may be that there's some external entropy production, and I'll say more about that in 1 second. That basically modifies it such that if I calculate eta, the parameter that needs to be 10 to the minus 10 or so, right, it's the number of baryons divided by the entropy, I can plug in all the constants needed to convert to the entropy. I get a very similar formula to the one before because n baryon is still sitting in the numerator, but there's an additional factor of the QCD temperature divided by the reheat temperature to the third power. It's the second to last factor in that middle equation. So what that represents is the fact that if there is entropy production after the phase transition, it will dilute the baryons that I produced during the phase transition.
Hey, Tim.
Yeah.
This formula depends on cosine theta effective.
Right.
So the theta effective is 0. You get the maximum baryon asymmetry. When there's no CP violation, you get.
Oh yeah, sorry. I made an approximation when I took a derivative, and that's why that looks like that. It's actually just an order 1 number that's a function of theta effective. It's not literally cosine.
Okay.
Thank you for catching that, actually. Good. So if I plug that all in and assume that there's an order 1 phase initially in theta effective, the eta that I get is 5 times 10 to the minus 9, and then times that factor that comes from the entropy production. So T QCD over T reheat to the cubed. So what's sort of amazing is that if I just ignore that production of entropy, I would get something very close to the baryon asymmetry that I want. And with very few free parameters. I mean, there's theta effective, which I assumed was order 1, but you know, clearly that just scales things up a little bit up and down. Most of the other parameters that went in there were either hadronic quantities or the weak coupling. There's really actually not much freedom in this equation. So it seems like if there's not much entropy production such that the reheat temperature is really the same as TQCD, I would get sort of the right ballpark for the baryon asymmetry. However, unfortunately, there is entropy production after this phase transition. And in fact, there's a lot of it. So what happens is, after the QCD phase transition, right down around a GeV or so, I break the electroweak symmetry, and I actually break it all the way to the full electroweak symmetry breaking that I see today. So the weak bosons get masses of order 100 GeV, and they decay very quickly. And the decay products then produce a lot of entropy, which dilutes the baryon asymmetry by a factor of about 100 GeV divided by 1 GeV cubed, or something like 1,000,000 or 1,000,000,000 times too much. So this was almost a great model with few free parameters. The problem is that if I think carefully about what happens to it, it doesn't quite work. I think also this problem was why this didn't get a huge amount of attention throughout the decades since it was proposed. It's actually very elegant and very cute, and many of us think that axions exist, so it's very natural. But the problem is it's just kind of far away from working. So what I'm going to do is now finally get to the contributions that Shada and I added to this story. And that is, rather than trying to delay the electroweak phase transition such that the sphalerons take place during the QCD phase transition, I want to have the QCD phase transition moved up so that it happens while the sphalerons are still active. So schematically what I'm doing is instead of having the QCD phase transition happen around, say, 1 GeV, I want it to happen around 100 GeV or even a TeV before the electroweak symmetry is broken. And now I still get the coincidence I need of the axion rolling to its minimum together with the sphalerons being active such that I can generate a baryon asymmetry. And just thinking about it, the baryogenesis story is basically the same as before, Of course, sorry, I should back up 1 second and say there's a lot of details I have to talk about how one does that and what that means. And of course, that is what the rest of this talk is about. But before I do that, I just wanted to close the parentheses on the baryogenesis story. It's pretty clear how this works then. I basically have the same formula as I did before, except that now TQCD has been set to basically to 1 TeV or 100 GeV. So TQCD and T reheat are basically the same temperature. There is no dilution from entropy production, or let's put it this way, there's an order 1 dilution from entropy production, such that I preserve the amount of baryons that I produced. And since I was already in the right ballpark, I stay in the right ballpark. In fact, I was maybe a little bit higher than I needed to be, and that could argue that you either need a little bit of dilution, or maybe theta bar was actually something like of order 10% rather than order 1. And of course, there's plenty that we need to think about to make that actually happen. So I'm going to switch gears now and talk about how to make QCD confined in the early universe. Maybe I'll ask if there are any questions before I move on. Okay, so I want to have QCD confined at about a TeV. How do I make that happen? So what we're envisioning is something like the following. The strong coupling is promoted, at least in part, to being a field. The parameters, so this field has some kind of potential. The parameters are such that somewhere above T electroweak, QCD gets strong and it confines. This is going to trigger electroweak symmetry breaking, including the Higgs VEV, just like it did in the previous discussion. And it generates a baryon asymmetry at high temperatures, just like we saw. The dilution is negligible because everything happens around the electroweak scale. But of course, then below the usual electroweak phase transition temperature and well before BBN, I have to have my field adjust itself to the usual strong coupling that we measure at low temperatures, such that QCD goes back to normal and everything looks fine in time to do BBN successfully. So what I'm going to do is model the strong coupling just using an effective field theory. So I modified the gluon kinetic term in the Lagrangian. If it's normalized such that the coupling has, the coupling is taken into the normalization of the gauge field, such that the kinetic term would be -1/4 1 over g squared times the gluon field strength squared. I'm going to add another term to that Lagrangian that has a new field phi. Phi is my field that basically controls the strong coupling constant, and that's divided by some energy scale m star. So effectively, if I go to the canonical normalization, this gives me an effective coupling for QCD g squared effective, which is equal to the g0 squared in the Lagrangian, and then divided by 1 plus g0 squared times the ratio of the phi VEV to m star. So phi could be something like a dilaton or maybe a radion in a theory with extra dimensions. You could actually just imagine it's some field that has some coupling to the gluons induced radiatively through a triangle diagram like the one that I've sketched here. You know, maybe you could add some vector-like quarks. They couple to phi. They're colored, so they also couple to gluons, and they would induce a triangle diagram like this, which looks at low energies like the effective theory I wrote down. G0 is the strong coupling, of course, in the absence of any phi VEV. It runs just like an ordinary QCD. So at one loop, I can write 1 over the effective strong coupling is equal to, so 1 over alpha naught is just the constant I get using the G naught and the Lagrangian. Then I have the ordinary 1 loop running for the coupling, which is written here with the 1 loop beta function. And then a correction that goes like 4 pi times the VEV of phi divided by m star. Right? The 4 pi is just because I went from 1 over g squared to 1 over alpha. Then I can invert this to find the scale at which QCD gets strong. And the scale at which QCD gets strong is something like lambda 0, right? The scale where it would have gotten strong in the absence of a phi VEV. And then there's an exponential dependence on the phi VEV multiplied by the beta function. If I imagine that there are 6 quarks, if I want to get a confinement at around a TeV, what I'd like is that the VEV of phi over m star is something like about -0.8 or so. So it's of order 1, but a little bit smaller than 1. This is maybe pushing the EFT as a description a little bit, though I think even replacing this with a full theory, it's not like it would break anything. It would just be more unwieldy to work with. But it's even not so bad that I would really think it's clearly problematic. It is true, though, that it's a fairly large ratio. If it was induced radiatively, it would require about 10 vector-like quarks at a mass of m star. So that tells you that m star could definitely not be too low, or you would start to see these things at the LHC. You'd probably need m star to be at least a couple TeV or so in order to avoid LHC bounds. I'm going to stay pretty agnostic about where the actual potential for phi comes from. That would be an interesting thing to follow up and try to get a pretty picture for it. I was just worried about making things work at all, and so I didn't worry so much about getting a pretty picture for it. If you write down something generic that's characterized by a single mass scale, obviously that produces a VEV around that scale. So you can imagine that the potential is just given by some polynomial in phi. So I put m's here just to characterize this single mass scale. And then the alpha, alpha 1, alpha 2, alpha 3, alpha 4 are just some constants, which I'm imagining are kind of order 1, which then characterize the specific potential. I guess you could probably redefine phi and get rid of the linear term if you wanted to. There is also actually a contribution to the phi potential that comes from the gluon condensate after QCD confines, so that's also part of the picture. Though it turns out it didn't seem like it was very important at the end of the day. You could sort of fairly easily get a phi VEV around m star without much tuning, right? It basically just boils down to, I could have this whole potential live about a factor of 10 less than m star, and then I would need about 10% fine tuning to get a VEV that's around m star itself. Once QCD gets strong, this last term in the potential also induces corrections of order lambda QCD, which is likely to be a fairly large correction to the VEV unless m is much larger than the lambda QCD itself. So to fix QCD after the electroweak transition, there needs to be some appropriate thermal corrections to the phi potential. This could just be as simple as imagining there are some states out there that have order 1 couplings to phi and masses around the TeV scale so that they decouple around 100 GeV. And the difference between having them in or out of the thermal potential is what you could imagine triggers phi to have one VEV or the other. Now, since all that really matters is that they have strong couplings to phi, these things don't need to be colored or electroweakly charged. LHC bounds on them are probably not strong. They could probably be dark matter if you wanted them to. I'll say a little bit about that possibility at the very end. Of course, while they're not particularly important for the story, they do play an important role for the phi phenomenology because they could be produced in its decays, or they could be part of how it gets produced at colliders and so forth. So the details do matter for the phenomenology. They just don't particularly matter from the point of view of whether or not QCD confines at the early universe. The phase transition is a little bit complicated because the Higgs VEV is induced via the chiral condensate through the Yukawa interactions. So modeling that took us a little bit of effort to kind of come up with a way to do it. It was also a lot of fun, I have to say. So what we're going to do basically is use chiral perturbation theory, which lives now around a TeV and has 6 massless or close to massless quark flavors in it, to try to estimate how big the Higgs VEV is that gets induced, how big the chiral condensate is, etc. So the Higgs VEV is induced via the chiral condensate through the Yukawa interactions, which should be naively dominated by the top quark. But what confused us was it wasn't initially clear to us that the induced VEV wasn't large enough that the top just decouples from the picture. So we weren't sure that that was actually the real picture to describe what happened. So we tried to be a little bit more careful, and what we did is we modeled the chiral symmetry breaking and the Higgs VEV together using a linear sigma model with an SU6 cross SU6 flavor symmetry. So this field capital pi right, represents my pions and also the chiral symmetry breaking VEVs, right? This is not the nonlinear representation of SU6 cross SU6 breaks down to SU6. It's actually got the full linearly realized SU6 cross SU6. So there's a kinetic term for those fields. There's some mass terms and some quartics. Naive dimensional analysis suggests that if I'm neglecting the Higgs, right, which I'm doing at this point, I should get a pion decay constant, which is about mu over one of the lambdas, and that this is something like the chiral perturbation theory cutoff divided by 4 pi. Then I want to improve this by including the Higgs and the Yukawas as SU6 cross SU6 breaking spurions. So what I do then is introduce the terms, I treat the Yukawa coupling, so this capital Y is a matrix with diagonal entries that are each given by the quark Yukawa coupling times the Higgs VEV, or the Higgs field if you want. And then I wrote down the leading operators that this allows one to include into the Lagrangian. The dominant one is the m tilde squared. It's like the analog of the pion mass in the usual chiral perturbation theory. If you continue to estimate the coefficients using naive dimensional analysis, the induced Higgs VEV turns out to be a little bit smaller than lambda QCD. That implies that the top mass that gets induced is itself of order lambda. So whether it really belongs in the effective theory description or not is kind of questionable. I'm sure that that probably has an order 1 impact on the actual VEV of the Higgs that's induced. But the results are probably okay at the order of magnitude level. And so if I put all of this together, this is a plot that shows the potential as a function of the Higgs VEV. And for lambda QCD confining at about a TeV, the chiral perturbation theory cutoff is taken to be 4 TeV. Then I get a Higgs VEV that turns out to be about 0.8 TeV. So it's again a little bit smaller than lambda QCD. It would be fun, but probably very computationally expensive to try to look at something like this on the lattice. So, all of that was just a way of trying to estimate when QCD confines, how big an electroweak symmetry breaking effect do I get from it. I still have to talk a little bit about how I'm going to then deconfine. Right now I've constructed a theory where QCD confines at a high temperature. I want to make sure that it then deconfines later on and goes back to normal. This is something that I looked at with Juna Kroon, Shada Epek, and Jessica Howard. So what we did here is we actually used the fact that I can write down interactions between the field phi, which has been helpfully relabeled here as S rather than phi, sorry about that, and the standard model Higgs, which is capital H. So I have a standard kind of potential that we saw before for the Higgs and also for the phi field. Those are the first 2 lines of equations. Then the last equation is just writing down the normalizable interactions between the singlet phi and the Higgs. And of course, there's something both linear in phi and also quadratic in phi that one can write down at that level. So this gets a little bit complicated, but what it does is result in a picture that looks something like what's schematically cartooned on the right-hand side of the slide. Looking at the temperature and starting from the left-hand side where the temperature is large, I start off in a place where the Higgs, where the phi VEV is such that I'm in the confined phase. As the temperature falls, the Higgs VEV itself evolves such that I end up getting to the deconfined transition. That's the green region on the plot. And then that proceeds down until QCD then confines again the way it normally would at 1 GeV. This is also shown as the set of arrows that are next to it. S is on the y-axis, right? Remember, S is phi, and the Higgs is on the x-axis. And what happens is we start off, the magenta arrow is when we confine the first time. We end up in a situation where, at least initially, it looks like there's a VEV for phi and no VEV for the Higgs. Of course, we just saw that the Higgs gets a tadpole and therefore gets a VEV very quickly after that. So that's what the blue arrow TC represents, where now I have a VEV for both S and the Higgs. So remember, S is phi and the Higgs. So you could really think of the magenta and blue arrows as happening pretty much simultaneously. And then at some point, because of the evolution of the Higgs VEV, I get triggered to move to a different value for the phi field, and that leads me to the standard model-like value, where the Higgs VEV is 246 GeV, and the phi VEV is some other value that corresponds to lambda QCD being 1 GeV. So that's all pretty complicated. It was kind of fun to analyze. The panels at the bottom just show snapshots at different temperatures. So the first one on the left is at a high temperature. You can see that there are 2 relatively degenerate minima at both a phi VEV of 0 and a phi VEV of about minus 1.5 TeV, where the Higgs VEV is close to 0 for both of them because we're at a high temperature. What happens is we end up living where the red dot is. That one is where we end up. Then as the universe cools, you move to something more like a picture that's in the middle panel. This is for a temperature that's close to the lambda QCD we chose for this parameter point. You can see that the Higgs Vev has turned on. So the blue dot has evolved over a little bit from where it was. And now a second minimum is developing where the red dot is, such that I end up transitioning into that minimum. And that's the last panel, which is right around the BBN temperature. You can see now there's no Vev for phi, so QCD has gone back to normal, and the Higgs Vev is about 250 GeV or so. There's lots of fun things when computing the thermal corrections. So for example, once QCD confines, the ingredients in the universe are no longer quarks. They are mesons, which are bosons and therefore have a different impact on the Higgs potential. And so the dominant contribution is coming from the top flavored mesons. I'm not going to say a whole lot about this because it is pretty complicated and it's not really super illuminating, but you can see more in our paper that's listed there. Then analyzing that parameter space by scanning. And so these parameters here on the x-axis and the y-axis are actually those potential terms which show how phi couples to the Higgs boson. In the upper left part of this slide, the last line, V of H and S. And sort of three regions one sees here. In the red and the blue regions, we actually don't realize the conditions that we want. We either have no first order phase transition, or we actually don't manage to get QCD back to normal by BBN. Those are the two regions respectively. And then in the white region, actually things happen in between those two scales such that you realize a parameter space that works for baryogenesis. The things that are overlaid, you can see that the blue colored lines are isotherms of the QCD, of the high energy QCD scale. For this particular parameter scan, it was a little bit lower than a TeV. It was more like around 100 GeV or 90 GeV. You can see what the Higgs Vev is at the time of confinement. That's the dotted black lines where it says VH equals 120, 160, 200 GeV. So you see that actually you get a Higgs Vev during confinement that's actually not that far away from the Higgs Vev that we have today. And then the gray bands that are diagonal, where it says MS equals something, tells me what the mass of the phi particle is for these theories. And so part of what we wanted to do was look at the phenomenology of phi. I'll say a little bit about that in a second. And you can see that it turns out for this parameter region to be somewhere sort of around 30 or 35 GeV. So it's heavy-ish, but it's definitely accessible to colliders. So I'll come back to that in 1 second, but I'm wrapping up now. So the outlook is the idea that QCD may have undergone a period of confinement in the early universe is really an interesting question. It highlights our general ignorance about the universe at times before BBN. It's kind of a playground where theorists can play. So the toy that I happen to play with is a theory that adjusts the strong forces coupling such that confinement occurs at around a TeV and then later relaxes to around 1 GeV after the dendritic phase transition. There are actually primordial gravitational wave signatures that could be associated with that first order phase transition of the early QCD confinement. We looked into this a little bit. It turns out it's very hard to model things in a way that you believe, and so we just kind of gave up on making a rigorous statement. But it's clear that there is actually some kind of gravitational wave signal which potentially could be produced. I mean, it'll be produced, it could potentially be observable. In a theory where the axions invoke to solve the strong CP problem, it appears to offer a viable baryogenesis option as well. There's lots of questions that still remain. So naively, the axion could possibly end up with the right relic density to be dark matter. If FA is adjusted appropriately to match the preferred theta initial. It does go through a period where the axion has a much larger mass, right? The axion mass gets scaled up along with everything else when QCD's scale gets increased. If you were to scale up lambda QCD as big as 10 to the 9 GeV or so, it would actually be large enough that most of the axions would decay during that period. Now, I was imagining lambda QCD being more like a TeV, and so then you would expect the axions would just start oscillating. They might go through some period of matter domination, but actually they would not have time to decay. And of course, the true hallmark of the dynamics I'm talking about is the singlet field phi that I talked about. Minimally, it has to couple to gluons. It also has Higgs-like interactions through mixing, right? Those terms in the potential that I introduced allow the Higgs particle to mix with the phi particle. In the parameter space we looked at, this mixing was always very small, less than about 10 to the minus 3 or so. Theta in this case is the theta of mix that describes mixing between Higgs and singlet. So as a result, this is small enough that the LHC would have a lot of difficulty seeing a deviation in the Higgs interactions because it's sort of typically sensitive to a few percent corrections, and these are sub-percent corrections. But there are still actually interesting things we can look at. So on the left panel of this figure, I've shown for the choice of M star being 5 TeV as a function of the singlet mass, what its width would be. So its width is typically large enough that it decays promptly. That's an important ingredient. And then if I look at the branching fraction, it typically likes to go to gluons. So that coupling that phi has with the gluons directly is typically the most important one. And that's just because the Higgs mixing is small enough that the other channels, right, which all go through Higgs mixing, are typically not that competitive. But if I do push things a little bit, I can actually get to a point where it also decays to something like BB bar or CC bar about half the time. And it also can decay to tau, you know, maybe some tens of percents of the time. If I put that together onto limits that I have, so this is as a function of the mass of the singlet on the x-axis, and then the mixing sine squared theta is the mixing angle between between phi and the Higgs times the branching ratio for the singlet into BB bar on the y-axis. And this just turns out to be a convenient parameter choice because it scales out most of the collider signature dependence. You can see the limits that were placed by LEP, by Opal, and by the LEP experiments collectively. Those are the orange regions that are ruled out. You can see where a Higgs factory would get you is the blue curve. A Z factory would be able to look at the process of something like Z goes to BB bar phi. That gives you the pink curve. And that's finally where you start to become sensitive to some of the parameter scans that we did. Those all live as these blue dots, and they're typically even low enough that a Higgs factory would have a lot of difficulty seeing them. Of course, phi also couples to gluons, so it can be produced at the LHC, and it could appear as a resonance in dijets, particularly if it's much heavier than some of the parameters I've been talking about here. There were some studies that were done by theorists, including Veronica Sands. They were looking at glue goes to some axion-like particle and then goes to ZZ. So that process would happen for us because we have some mixing with the Higgs. They were also looking for low masses. And of course, if the mass of the axion-like particle is low enough, then your limit doesn't really depend very much on that mass. Instead, really what it just depends on is the size of the coupling because you're going off shell to produce ZZ in the final state. So they produced this plot where you see the mass of the axion-like particle is on the x-axis. The coupling of the axion-like particle to ZZ is on the y-axis. They can rule things out using a variety of LHC and lower energy searches. What they're adding to it is really this hatched region from LHC mono Z. Our parameter space, though, and if I trace it onto these parameters, we have a mass that's sort of around tens of GeV, and the coupling turns out to be something like about a tenth or so in 1 over TeV for the coupling to Z bosons. That's roughly where the big black star is. So it's close enough that maybe the LHC will get there, but it hasn't gotten there yet. And of course, there could be other, you know, maybe the K modes to dark matter if I introduce more particles coupled to the singlet. So just the very last thing I wanted to mention, if I think about that seriously, let's imagine that instead of trying to use the axion as dark matter, I just say that there is some other WIMP dark matter that couples to quarks via a scalar portal. Maybe there's some dark particles that couple to phi, and then phi is its portal to the standard model. Let's also imagine the masses of these particles are such that they freeze out during the confined phase. It turns out the relic density can actually be very different from our naive expectations. So the thing that was obvious that made us start thinking about it in the first place is the fact that if you freeze out during confinement, the thing you're annihilating into would be mesons rather than quarks. And that's a pretty big actually difference because the effective couplings to mesons know about the QCD scale, and so therefore the interactions look to be very different in size. Another interesting thing is that the dark matter mass gets shifted by Cargill symmetry breaking. If chi bar couples to QQ bar, then when QQ bar gets a VEV, the dark matter mass shifts. So you actually have a theory where the dark matter has a different mass during the time it's freezing out than what it would have today. The upshot of all of this is that, this is shown in the figures, so maybe actually the lower figure is the more interesting one to focus on. There's the mass of the dark matter at 0 temperature, so going from a few GeV up to about a TeV or so. The standard case of a WIMP is shown as the dark solid line, and what's plotted is the value of the interaction you would need to realize the relic density that we see today. So basically, this solid line is showing you what coupling strength you need to realize the relic density we see today as a function of mass. The big threshold you see around the top mass is just because annihilation to TT bar is turning on. And you know, famously, WIMPs are in trouble. That solid line is all excluded by xenon 1 ton. In this plot, right, smaller values of the scale MS are stronger interactions. So xenon excludes everything below the blue dashed line. Then when I go to the theory where the freeze out is through the exact same interaction, but at a time when QCD is confined, my target curves actually become the pair of the black and red dashed and dotted lines. Those are for 2 different values of scaling up the QCD scale. They are typically not excluded by xenon. And the reason is at the time of freeze out, the dark matter has a different mass and a stronger interaction such that my target region is actually shifted today compared to what it looks like today when QCD has gone back to normal. So thank you very much. Silence. Well, I'm not going to try to win a staring contest against John because I've never won a staring contest against John.
We're going to move to an informal discussion after the question period.
Okay.
But
in your asymmetry, well, the Sphaleron asymmetry formula, it has all these QCD parameters like M eta prime and F pi and well M pi and so on.
Yeah.
See. Oh, they cancel, so it doesn't matter, I guess.
And they leave behind some order 1 number, but that's right. They don't really matter very much.
So about these slides, I have a very simple question. I'm trying to understand this formula. For example, I can understand is that let's say if this formula says if the pion mass is 0, there's no baryon symmetry because in that sense the up quark or down quark mass is 0, then you don't have this round CP problem. So why is lambda to the why is lambda to the 7 order? This 7 order is there any meaning about this 7?
Yeah, here, let me back up a second to where I first derived this, and then it's a little clearer.
Okay.
If you look at the very bottom of this slide, there's the formula for the axion mass as a function of temperature.
Okay.
That's where the lambda over T to the 7th comes from.
Okay, so why this formula?
Oh, why is it 7? I mean, it's a statement, right, about the topological susceptibility of QCD as a function of temperature. It has something to do with the way the instantons react to the finite temperature theory, but I don't really know much more about it than that.
Okay, so it's fine. Okay.
so can you say something more about I'm confused about when the Cargill symmetry breaking happens and it triggers electroweak symmetry breaking. I guess in your scenario, I guess it makes sense, but in the old scenario, why it would shift the Higgs VEV by some small amount, and then wouldn't it still have to tunnel?
Yeah, actually what happens is, though, I think the best way to understand it is that, sorry, I'm backing up. No, not there. I think the best way to understand it is that you've got this big barrier, and it turns out though that adding just that little tadpole is enough to kind of wrench you over the barrier. So you're right that naively it would be a small change. But what it does is it makes the transition fast enough that it starts to happen.
Okay. So in your case, is there a period where you start with longitudinal modes or pions and then they switch over?
Oh yeah, that's interesting. I didn't actually look into that in detail, but yeah, there's something like that that's happening. That's right. Yeah, I'd have to think about that somewhat. I haven't really spent any time on it.
Okay. Okay, if there's no more questions, last chance. Let's thank Tim again.
Thank you.